So now we're going to talk about radioactive decays, the neutron-proton ratios, and the band/valley of stability. So now we're going to come back and we're going to do the details. Okay, we're going to do the details. So once again, when I look at my band, I know that my band is only, the black band is only 15% of all nuclei or all isotopes. 85% are unstable. So what we'll do here is that we're going to look at the stable nuclei first. And what do we know about them? So most nuclei that are stable have their NP values as follows. Okay, so we can only go up to lead. So here we go. So the first range here is we're going to talk about nuclei with atomic numbers less than 20. So when we look at these, we say that if you have an atomic number that's less than 20, then what this tells you here is that the most stable have an NP value that's approximately equal to 1. That's what it means to be stable. So then if I go to the next one, we're going to talk about nuclei with atomic numbers between 20 and 82. What's 20? It's calcium. What's 82? It's lead. So let's go look at this thing. So if I look at this thing, if I have atoms that are greater than calcium, so that means its atomic number so this guy right here is calcium. This number here is lead. So if I'm between there, what you're going to find here is that we saw that there was a range. So we said that the most stable have two numbers here. So if you had NP values of the order of about 1, I don't know, 1.2, 1.3, we saw that these were the mid-weight ones. So these guys were the mid-weight nuclei. And then if you had an NP, so if you look at lead, this guy's about 1.5. So these are the very heavy nuclei. So if this is the case here, then we know that this is what we mean when we're talking about stable atoms. That's what they have to follow. So the question is that I keep saying that nuclei follow a very systematic process. They try to reach the band of stability by doing however many decays they got to do. And so we want to look at the NP values of the following thing here. So if I go and I look at these things here, so now there are 3 effective areas. On the band of stability. So I think I have it right here. I do. Fantastic. So if I look at this, there's 3. I clearly have the turquoise region. So the turquoise region is special. The turquoise region, as soon as you see the turquoise region, you immediately have to think beta decay. Okay? Beta decay. Beta decay. So why is beta decay so important here? Because they have what? They have too many neutrons, and they have too few protons. So if you look at a beta decay right here, okay, if you look at a beta decay, here's what you got to find here. What you're going to find here is that beta decay, what does it do? So to reach stability quickly, what it does here is it increases I'm sorry, I do not want to say that. It decreases neutrons and it increases protons. So then that's the fastest way to stability. Because now instead of being above the line, you're now going down towards the line. So this process then, so then a nuclei, now a nuclei that starts above the black line now falls towards the black line. And that's what we mean by the turquoise region. So when I look at this turquoise region, right, we're talking about, I mean, we've already done this numerous times. So we know that this region here, that's what we mean right there. This is what we mean by beta decay. And so when I look at my valley, it looks like this. I'm seeing that right here, here's my band of stability here. So that means that these guys are moving down. And when they go in this direction, they decrease the number of neutrons and increase the number of protons. So then we go to the next region. The next region here is the orange region. And this is the region of inverse beta decay. And so in this region, what do we have here? We have, in this case, we have too many protons, and we have too few neutrons. So you see that these guys are below the band. So when you have an inverse beta decay, we see that it does what? It decreases protons, but at the same time, it increases neutrons. So then in this situation, what you're seeing here is that when I look at this orange region right here, right? This is the region of inverse beta. So then what happens here is that in this situation, what we're seeing here is that nuclei start below the black line. Now move upwards towards the black line. But that's not the way we see it in the band of stability, because now what you're seeing here is that these guys are doing what? They're falling. That's what I need. I need orange here. So now they're falling. Ooh, that is really thin. Okay, so they're falling, and as they fall, they're falling along that path. So that's what you're doing right there when you do that. So that's what they call the drip lines. And then the last one is the yellow region. And what you find with these yellow region is that this is the region of alpha decay. Now, what's special about alpha decay? Well, it has the following thing. It has too many neutrons, and it also has too many protons. So what it's doing here is alpha decay doesn't decrease, here you could see that the pattern is that you're only decreasing one at a time. Not true. So what you're seeing here is that it decreases both neutrons and it decreases protons simultaneously. And so what you're seeing here is that when I look at the band of stability, you could see here is that you have this region. And there's some yellow around, but these are the regions of the alphas. And so they're way above the black line of stability. And the image that I showed you before is that they're like the mountainous region. And so what you're seeing here is that in this case, these nuclei start above the black line and move downwards towards the black line of stability.